Okay guys, in this last video on electrochemistry, we're going to be looking at electrolytic cells. Recall from our previous discussion that a voltaic cell is a type of electrochemical cell that exploits a spontaneous redox reaction to produce electricity, whereas an electrolytic cell is one that uses an external power source to drive a non-spontaneous redox reaction. So we're going to talk about different types of electrolytic cells, and then we're going to do some calculations involving electrolysis. So the first type of electrolytic cell we're going to talk about involves the electrolysis of molten salts. And so you can melt down ionic compounds at very high temperatures. For example, sodium chloride can be melted at around 800 degrees Celsius. If you then dip two electrodes into the molten salt and then apply an external power source, you can drive the following reactions to occur. You can drive the liquid chloride ions to produce chlorine gas, and you can drive the sodium liquid ions into metallic sodium. And this is actually how certain metals and gases are produced industrially by using electrolysis of molten salts. The second type of electrolytic cell that we're going to talk about involves aqueous electrolysis. And so this is where you have your ionic compounds dissolved in aqueous solution, and there you have to consider not only the half reactions involving the solutes, but you also have to consider half reactions involving water that can occur at the electrode surfaces. And so the rule is that the reactions with the more positive electrode potential are preferred. So I say more positive or less negative electrode potential are preferred. And so I'm going to show you how to use that rule in some of the upcoming examples. First, I wanted to go over the possible oxidation and reduction of water. So in an aqueous solution, if you dip two electrodes into it and zap it with electricity, it is possible that the water could be oxidized from water to oxygen. Okay, and so here the oxidation number of oxygen in the water is -2. Here it's 0, so this is the oxidation of water to oxygen. This is a possible reaction at the anode of your electrolytic cell for aqueous solutions. Alternatively, at the cathode, it could be that the water is reduced to hydrogen gas. And so here the oxidation number of hydrogen is +1, and it's 0 in the form of molecular hydrogen. And so this is the possible reduction reaction of water at the cathode. You have to take these into consideration when you try to determine what's going to happen when you try to electrolyze an aqueous solution. And so here is an example of what that might look like. So let's suppose that you had a sulfuric acid solution here. You've got two electrodes, you've got an anode and a cathode, and we want to consider what possible half reactions can occur at these two electrodes. And so you need to consider all of the species that are present. So you've got acid protons that are present, you've got sulfate ions present, and then water is present in the solution. And you want to ask yourself, what reactions can occur at the anode? Well, remember that oxidation occurs at the anode, and so H plus can't be further oxidized. So H plus is not going to be involved in any of the reactions at the anode. However, the sulfate could be oxidized to this disulfate species. Water could also be oxidized, and you need to be able to figure out what could be the products if you oxidize water. Well, as I said, H plus, or hydrogen here, has a +1 oxidation state in water, and it can't be raised any further than that. However, the oxygen is in a -2 oxidation state, and you can raise the oxidation number of oxygen from -2 to 0. And so this is the possible reaction that could occur involving water at the anode. For the cathode, you could end up reducing the H plus to H2. There's nothing you can do with the sulfate at the cathode, but you could reduce the water to H2 as well. And so you can look up the reduction potentials for these reactions. You can find them in your table of electrochemical reactions, and you'll get a value of 0 for the H plus, and you'll get a value of minus 0.83 volts for the reduction of water. And the rule is, the more positive the electrode potential, the reaction with the more positive electrode potential is the preferred reaction. So in the case of the cathode here, the more positive electrode potential is where the reduction potential is 0 volts. Okay, so this is that's why I put a star here. This is the preferred reaction at the cathode. For the anode, there's one slight difference. Okay, and it has to do with the subtlety involving the difference between the electrode potential versus the reduction potential. Okay, they're not quite the same thing. For the cathode, the electrode potential is the reduction potential, but for the anode, the electrode potential is the oxidation potential, which is minus the reduction potential. So notice when I'm discussing the half reactions at the anode, I specifically put a subscript OX to indicate that these are the oxidation potentials, and these are minus the value that you would look up in the table of reduction values. So you're not going to find these two reactions listed in the cell potential tables because these are oxidations. What you will, however, find is the reverse of these reactions. And so what I've done is I've taken those reduction potentials for the reverse of the reactions and I've changed the sign so that they become the oxidation potentials. And then I can apply my rule that the more positive, less negative value is going to be the preferred reaction. And we see that that would be for this second reaction here involving the oxidation of water to oxygen. So this is going to be the preferred reaction at our anode. It's going to be favored over this first reaction. So now that I know the two reactions that are going to be occurring at my electrodes, I can then recombine these two half reactions. I need to multiply this equation by 2, and I can do some cancellation, but in the end what I'm going to get is the decomposition of water. We call this, in electrochemistry, we call it the electrolysis of water, where you're splitting water into hydrogen gas and oxygen gas. Essentially, the sulfuric acid that's in the solution really doesn't play a role at all in this electrolysis. You would get the same result if you just electrolyzed pure water. Here, let's look at a different example. This one involves the electrolysis of an aqueous sodium chloride solution. Consider what species you have. You've got sodium cations, chloride anions, and then you've also got water. Okay, so let's look at the possible reactions at the anode. Chloride could be oxidized to diatomic chlorine. You go from -1 oxidation state to an oxidation state of 0. Likewise, the water could be oxidized as well. In this case, these are the oxidation potentials. So these are minus the values of the reduction potentials that you get from the table of electrochemical reactions. And what I'm pointing out here is that these numbers are pretty close together. Okay, and so in this case, it's hard to make a call as to which one of them is going to be preferred. And the answer is that it's going to depend upon the conditions under which the electrolysis is carried out. So if you've got a dilute solution, meaning that you don't have very much chloride present in the solution, then the water oxidation is going to be preferred. However, if you have a very concentrated solution that has a lot of chloride present, then you are going to get a significant amount of chloride being oxidized as well. So this is called overvoltage. Okay. For the cathode, however, things are a bit easier to see. If you consider that the sodium could be oxidized to sodium metal, and the water could be, the sodium could be reduced to sodium metal, and the water could be reduced to hydrogen gas. Here, there's a much bigger difference between the two reduction potentials, and the more positive, less negative value is the preferred one. In this case, it's the reduction of water to hydrogen, so this reaction is going to beat out this reaction up here by a large margin. Here's an example problem for us to think about. So we're thinking about the electrolysis of copper 2 sulfate. So you want to think about what you have in solution. You've got copper 2 ions, sulfate ions, and water. And so you want to consider what are the possible reactions that can occur at the anode. Okay, and so water could be oxidized to oxygen, and also we can consider this oxidation of sulfate going to the disulfate ion. So notice that here's what you find in your table of half reactions. The reaction that occurs at the anode would be the reverse of that. And so what I've then done is I've taken the reverse reactions from the reduction table, and then I've taken their reduction potentials and changed their sign to give me the oxidation potential at the anode. And then to choose which one would be preferred, I look to the one that is more positive or less negative, and that would be the second one here. So the oxidation of water to oxygen is going to be preferred over the oxidation of sulfate to disulfate. At the cathode, we could end up reducing copper 2 to copper 0, or we could reduce the water down to hydrogen. And since these are reduction reactions, I can pull those numbers directly from the table without changing their sign, and then I can make my choice. The more positive reduction potential is going to give me the reaction that's being preferred. And so in this case, that would involve the reduction of copper will be preferred over the reduction of water. And so these are now my two half reactions. I can recombine them by multiplying this equation by 2 and adding it to that equation, and that's going to give me this redox reaction here. So this is the redox reaction that's going to occur in this electrolytic cell. Here's another example. I think I'm just going to leave this one to you guys to try out, and I'm going to move on to the last topic here. This one involves electroplating of metals. So it's an application of electrochemistry. Oftentimes you have a metal part, and you'd like to coat that metal part with a different metal, either to help protect that metal, the metal part, or to make it more lustrous and shiny so that people want to buy it. So for example, decorative spoons are often made out of a cheaper metal like zinc, and then they're plated with something pretty like silver. So here is the reaction that's going on. You're taking zinc ions from a solution and you are depositing them on an electrode in the form of a solid coating. Here's an example of what it might look like. You've got your anode, the silver in this case. There's a silver nitrate solution. Here is perhaps your cheaper metal, whatever this spoon is made out of, and then you've got an external power source that then drives the silver ions to form silver to be reduced on the cheaper electrode, the cathode in this case. Faraday's laws are used to describe the stoichiometry of electrolysis. They're pretty simple, so we don't really need to worry about the formal statements of them. What I want to point out is you're going to be working with units of electric current in these types of problems, which involve charge per unit time. And the types of conversions that you have to do are something like this. You have to be able to take an electric current that's applied for a certain amount of time. That gives you an amount of charge that's been used in the in the electrolysis procedure, you can convert that to moles of electrons. Once you know the number of moles of electrons, you can then convert that to moles of metal, and then typically grams of metal you could then calculate. You also need to be able to go the other way. Let's suppose that you need to deposit a certain number of moles of metal. That's going to require you to transfer a certain number of moles of electrons. You can convert that to charge. And then for a given amount of time needed to prep the part, you can determine what the electric current is that you would need. Or given that the current is fixed, you could calculate the time it would take to electroplate that much metal. And so here are what these, here's one example. So we have, we're doing some electroplating of silver. Okay, we've got a current of 10.23 amps that we pass through the electrolytic circuit for about an hour. And they want to know what amount of mass of silver was deposited on the cathode. So here is the half reaction of interest. You've got the silver nitrate solution. The silver is being deposited as silver solid. We are being asked to convert the current to charge, then from charge to moles of electrons, then from moles of electrons to moles of silver, and then we can convert to grams of silver. So we take the 10 amps, that's 10 coulombs per second, multiply by 1 hour, 3,600 seconds, and so this gives us the charge that's being transferred, the coulombs. We divide by the Faraday constant to convert that to moles of electrons. And then just looking at the stoichiometry, it's 1 to 1. So for every mole of electrons that's transferred, we're going to get a mole of silver. So that's the ratio there. And then lastly, we multiply by the molar mass of metallic silver to give us the amount in grams of silver that was deposited, 40.2 grams in this case. In this problem, we're being asked to go the other way, and it's kind of there's a bit more of a difficult setup involved, but anyway, we'll go through it. So here we are taking, we're trying to deposit chromium. Okay, so we're making a chrome-plated part here, and we need to put a layer of 0.01 millimeter layer of chromium on this part, and the part has a surface area of 3.3 square meters. Okay. How long would it take to deposit this layer of chromium if the current involved is 33.6 amps? By the way, the density of chromium metal is 7.19 grams per cubic centimeter. Okay, so this chromium layer has a volume, right? It has a surface area times the height, gives you the volume of chromium that needs to be deposited. You can then use the density of chromium and that volume to figure out the grams of chromium you need to deposit. Once you know the grams of chromium, you can convert that to moles of electrons, then to charge, and then using the current, you can convert that to the seconds required to do the electroplating. So this first calculation involves converting the density and the dimensions of the part to grams. Okay, so this is the calculation for the mass of the chromium. Here I've got the thickness of the part times which I've expressed in meters. Then I've got the surface area of the part expressed as meters squared. This is a conversion factor from cubic meters to cubic centimeters, and then I can use the density, which is expressed in grams per cubic centimeters, to give me the mass in grams. So we need 237 grams of chromium to be deposited. So then you take the grams of chromium, divide by the molar mass of chromium to get the moles of chromium. We'll notice I didn't include it, but you're going from chromium 3 to chromium 0, so there's 3 moles of electrons involved in that half reaction, so it's 3 to 1 ratio. Then we use the Faraday constant to convert from moles of electrons to coulombs, so that's given here. And finally, we divide by the electric current to get the time, so 3.9 times 10 to the 4 seconds, which if you convert to hours is about 11 hours this part needs to spend in the electrolytic cell at that current in order to get that much chromium deposited on the part. Okay, so I think that's the end of the video. That's the end of the lectures for the course. So I'm going to shut up now.